Okay, hi everyone. It's Mr. Mellinger, and this is the assignment, day 14, February 14th of 2019. This is an assignment where you're being introduced to the concept of solutions, particularly aqueous solutions, solutions in water, and how do you express the concentrations of a solution. If you have a pure solution, or excuse me, a pure liquid such as water, then you don't need to deal with this. It's just water. But if you mix something in it, say lemonade mix, powdered lemonade mix, then you would need to, there would be some sort of concentration that's expressed on the container of the lemonade mix. It might say 2 scoops per quart of water. That would be an expression of concentration. The lemonade mix is called the solute. It's what's being dissolved. And the water would be the solvent. It's what's doing the dissolving. And when you put the two together, it's called the solution. Maybe the most common one that we might use for examples is sodium chloride or table salt in water. So salt water, mixing salt into water. So there has to be a way of expressing how much of the solute, what's getting dissolved, is mixed in with the solvent. Okay, so we discussed some of the ways of measuring concentration. The most common one used in chemistry, you'll find, is molarity. And molarity is expressed as moles of, and you should add this onto your sheet here, moles of solute divided by liters of solution. That's not the water, that's the mixture of, in the case of salt water, of the salt and the water together. Okay. Another one is molality. The two names sound the same, they're different. This is also moles of solute, but it's over kilograms. It's a mass of water, and that's the mass of the solvent, in this case water, not of the solution. So this one is the solution, this one is the solvent, which in the case of salt water would be the water. Okay. Another one we use is mass percent. And that's the grams of the solute over the grams of the solution. So in the case of salt water, it would be how many grams of salt do you have divided by how many grams of salt plus grams of water together. And then you multiply that by 100% to make that a percentage. The last one we'll talk about here is mole fraction. It's similar to mass percent, except it's not expressed as a percentage, it's simply expressed as a fraction. The reason is simply, as you see when we get into problems later on in this course, we use mole fraction, we don't use mole percent. That's just not an important measure of concentration. So that is simply the moles of one of the solutes, assuming that there's just one solute, it's the moles of the solute over the moles of the solute and the moles of the solution. So moles of salt divided by moles of salt plus moles of water in the case of salt water. There are some important conversions you should be aware of. And the first one is, for anything, 1 cubic centimeter is equal to 1 milliliter. Those are both measures of volume. Sometimes things are expressed in cubic centimeters or centimeters cubed, and sometimes in terms of milliliters, but they're exactly the same volume. Now, there's a couple that are, there's one that's particularly important that it applies only to pure water. And that is that 1 gram of pure water is equal to 1 milliliter of pure water. Or you could say 1 gram of pure water is equal to 1 cubic centimeter of pure water. In other words, it converts a mass, basically a weight of water, into a volume of water, which is a nice thing to be able to do when you want to, when you have a problem that requires that you be able to make that conversion. On a little bit larger scale, 1 liter is equal to 1 kilogram, and that's only true of water. Okay, density is the amount of mass that fits into a certain unit of volume. So if you have a cubic centimeter of cotton candy, it's going to be less dense than a cubic centimeter of iron, because iron has much more mass in the same amount of volume. Similarly, if you have let's say a liter of cotton candy, and then you compress that down into 1 cubic centimeter of cotton candy, you have the same mass. You didn't change how much it weighs, but you changed the amount of volume it's taking up. You made the volume much smaller, so that would also be a higher density. Just think of people in a room. If you're in a room with 10 people, and then suddenly a lot of people come in the door and now there's 100 people, the room is much more densely packed than it was before. There's more people in the same amount of area or same amount of volume than there was before. Okay, so let's get on to our problems. There's quite a few of them to do. You have a long weekend, and I'm hoping you break this assignment up over the weekend. I'm going to move through these problems fairly quickly. Remember, you can always pause the video and go back, and you should always try to do a problem, at least give it a minute or two thought before you just watch the answer, and see if you can figure these out on your own. Eventually you will be able to. At first these problems are going to seem very difficult, but eventually if you practice them and you really try, they will come through to you. Now the first page of problems, 1 through 4, are fairly straightforward. Your next test is not going to is only going to include these types of problems. They're pretty much just plug in the numbers type of problems. The more complicated ones that we're going to do in the second part of this and the later part of this session, you will not be asked to do this week, but you will in about a month. Okay, so try to do those as best you can. Okay, so here we go. What is the molarity of 8.2 grams of sodium chloride mixed in 1 liter solution? So way over here on the right, we're going to write, we're looking for molarity, which is moles of NaCl. You go back to your reference page on the front, divided by liters of solution. Now we could write NaCl plus H2O for solution, but it's kind of tedious to do that. We're just going to call it solution, SOLN. So this is what we're trying to find. Okay, we start off with 84.2 grams. Okay, and of course you're going to have to compute your molar mass of NaCl, and so I'm going to go ahead and write that up here. It's 1 mole of NaCl equals, and you'll pretty much learn this number pretty soon because we use it quite a bit, 58.44 grams of NaCl. Okay, so we need to convert from grams to moles. And by the way, we should put on the bottom here that it was 84.2 grams of NaCl in 1 liter. And that's important because that's part of our molarity equation. Okay, so here we go. Now it's just a simple conversion. There's 1 mole of NaCl for every 58.44 grams. And when you run the number on that, you end up with 1.44 moles of NaCl. Well, we have it, I'm sorry, let me just already have that over there. So I'm going to erase that. 1.44 moles of NaCl for every liter of solution, and really the way you should properly express that final answer is 1.44 molar is the way it would be said. Okay, so that's the concentration of salt in water, is 1.44 moles of salt for every liter of water. Okay, the next question is identical except the numbers are changed. So we're looking for molarity, 56.6 grams of sodium hydroxide in 2 liters of solution. So we have moles of NaOH for every liter of solution. Okay, for every liter of solution, we're starting off with 56.6 grams sodium hydroxide for every 2 liters of solution. That's the concentration. And again, we need to have a molar mass, and that's going to be 1 mole of sodium hydroxide is 40 grams. Okay, so we go ahead and put that in here, 1 mole. Okay, and when we crunch the numbers on that, we get an answer of 0.706 moles of sodium hydroxide per liter of solution. And that, of course, is 0.706 molar. Okay, There we go. So far, so good. Pretty much just plugging in numbers and doing mass to gram or mass to moles conversion that we've been doing throughout this class. Okay, next we're looking at molality. Okay, so let's write down. Let's be sure we're clear what molality is. It's moles of solute. In this case, it's HCl, hydrochloric acid, for every kilogram of the solvent. In this case, it's water. It's not of the solution, it's just of the solvent itself, water. So what we're trying to shoot for is kilograms of water, moles of HCl. So we're starting off with 12.7 grams of HCl. And it says we have that in 5 kilograms of water. Okay, now we can do, we need to get from grams of HCl to moles, so let's take care of that first. We need to have our molar mass. So I'm going to write that over here. Let me draw a line between these problems. So 1 mole of HCl equals 36.46 grams of HCl. Again, if you're having problems doing that, come and see me and let's practice some of how do we get this, okay? It's just getting straight off the periodic table from the atomic masses or the molar masses. Okay, so here we go. So it's 1 mole Okay, so grams of HCl and grams of HCl cancels. We have moles of HCl, which is what we want on the top. Now we got to get 5 kilograms of H2O to 1 kilogram of H2O. Well, we're just going to do a division then, okay? So if we multiply this by this, divided by 36.46 divided by 5, that will give us moles per 1 kilogram of H2O. And when you do that, that's going to give you an answer of 0.070 moles of HCl per kilogram of water, or you can write that it's molal, small m. So 0.070 molal is the way that would be stated. Okay, next one, same thing, molality. And I inadvertently gave you the wrong numbers here. I remember I gave you some numbers in class, but let's just skip that one. And we'll move on to the next one, okay? Just go ahead and do the numbers I gave you in class. I'm going to move on from that. Okay, here we go. We're on to 3A. Now we're looking for mass percent. So that's going to be the grams of the solute. It could be the solvent, but in this case it's the solute over the grams of the total solution. So that's the magnesium plus the water together. So let's write that down. It's mass, in this case, of magnesium divided by mass of magnesium plus, let's get that to magnesium, mass of water. You add those two together in the denominator. You want the mass of the whole solution, and then you have to multiply by 100%. Just means multiply by 100 and put the percent sign on the end. Okay, so everything is already, the only conversion we need to make is we need to get from kilograms to grams of water. We can't add grams and kilograms. You either have to have it all in kilograms or all in grams. It really doesn't matter which way you go, but we're used to dealing in grams, so we're going to convert it. So let's just do that over here. 2.4 kilograms of water times 1,000 grams. For every 1 kilogram, cancel kilograms, and you end up with 2,400 grams. Okay, so now we're ready to set up the equation. It's 75, which is the mass of the magnesium, divided by the total mass, which is 75, the mass of the magnesium, plus 2,400, the mass of the water. And that gives us an answer of and times 100%, let's not forget that. and that gives us 3.03%. So magnesium, of the mass of that entire solution, is 3.3% of the mass of the entire solution. Okay, be sure you can see that over there. Sorry, it went off screen a little. Okay. Okay, next, same thing, 3B. All right, so everything here, it's easier. Everything's already in grams. So we're going to take the 82 grams of the nitric oxide and divide by that same mass plus H2O. Oops, put in the number. 2465 grams. Okay, and when we run that number, we end up, and times 100% again, we run that number, we end up with 3.22% by mass. I'll write out the entire answer this time rather than just the number, of NO. Okay, 3.22% by mass of NO. Okay, all right. Now we're going to go on to a mole fraction. It's very much like percent mass, except you deal with moles and not with grams, and you don't convert it to a percentage. You just leave it as a decimal number. Okay, so here we go. Let's do this. The first thing we need to do is, everything though is given to us in grams here, as you can see. So we're going to need to do several conversions here. All right, so I'm going to come way over here to the side, and I'm going to try to do those conversions over here. So 1 mole of MgO equals, excuse me, equals 40.31 grams of MgO. Okay, 1 mole of HBr equals 80.91 grams of HBr. Okay, and 1 mole of water is equal to, this is one you'll have memorized if you don't already, 18.02 grams of H2O. So there's our 3 molar mass conversions. Okay, now let's figure out what the mole fraction of MgO is. So how many moles of MgO are there? Then we need to figure out how many moles of HBr, and then how many moles of water. We got to get all of these things turned into moles using these over here. Okay, so let's go ahead and just do this one here. So what is the mole fraction? I'm going to start way over on the left here, be sure I don't run out of space. So I have 75.3 grams of magnesium oxide times our molar mass conversion. We need to convert it into moles of magnesium oxide divided by 40.31 grams of magnesium oxide. And when we do that, we find out that we have 1.84 moles of magnesium oxide. Okay, next is same thing for, hydrobromic acid, and that's going to be 45.0 grams HBr times 1 mole of HBr, just our molar mass conversion. And over here it's 80.91 grams HBr. Okay, and grams cancels, you end up with moles, and you do the math on that one, and you get 0.556 moles of HBr. Oops, hold that up like that. Okay, so finally I've got to figure out the number of moles of water. So we're starting off with 112 grams of water, and the molar mass is 1 mole. For every 18.02 grams of H2O. And that gives us a molar mass of water of 6.22 moles. Okay, so now the first question is find the mole fraction of MgO. Now I didn't leave you with enough space here to do this problem, so I'm going to let you off the hook. Just do 4A MgO. You would do 4B the same way, except you would substitute the moles of HBr. But let's just do it for. So we're just going to do this one. Okay. So what we have is 1.84 moles of MgO divided by 6.22 moles of H2O plus 1.84 moles of MgO plus, and I'm running out of space here, I'm going to write it down here, 0.566 moles of HBr. Okay, so you add those three numbers in the denominator and divide this number by all three of those added up. And that is going to give you a mole fraction, which is symbolized by the big X. It's called chi in Greek, and it's 0.213 fraction for MgO. That's the fraction of the solution that's MgO. You can do HBr on your own, or you don't have to do it at all, because I didn't give you enough space. But anyway, that's how you do those, okay? Don't worry, we'll do more of them in the future. Okay, we're back. We're ready to move on to some more complex problems. I'm just going to kind of alleviate your concern that on this Friday, on February the 22nd, you're going to have a test. None of these problems from 5A on are going to be on the test. It's going to be the ones you just did. They're pretty much plug in the numbers type of problems. These, though, are almost AP level type problems. And so we're going to I want to just expose you to them. I want you to take them seriously. I want you to try them and try to understand them as best you can. But don't panic if you don't understand them right away. You will eventually need to, however, to do chemistry. A lot of our chemistry is done in solution, and we need to understand these concentration problems, how to do this kind of stoichiometry with concentrations of solutions. Okay, so here we go. Seawater has a density of 1.027 grams per milliliter. So let's break that down here. Seawater is our solution. So that means the density, we can use capital D, or there's a Greek letter rho that sometimes used, but we're going to use capital D, is 1.027 grams of solution. That's our seawater for every 1 milliliter of solution. So you want to attach that term solution so you know what we're talking about. It's grams of solution to milliliters of solution is what that's relating to. And it's comprised mainly of sodium chloride, which is NaCl. Okay, so before I know whether I need to even do this or not, I'm going to go ahead and up here on the top do my molar conversion for sodium chloride. So 1 mole NaCl is equal to 58.44 grams of NaCl. Okay, right there. All right. What is the molarity of a solution that has a 3.50 mass percent of sodium chloride? Okay, so two things we're going to do here. we're going to say, what is molarity? Break it down into its fundamental units. You're trying to end up in these fundamental units: moles of NaCl per liter of solution. So those are the units of measure we're shooting for our final answer. Now, whenever you have a mass percent problem, there's a little trick to use to solve that. You just you make it up out of whole cloth, a fictional amount of the substance, okay, a fictional mass. And so what we're going to do is we're going to take the usual mass that's almost always used is a 100-gram sample. So what it's saying, 3.5 mass percent, is saying this, that if you have 3.5 grams of NaCl and it's 3.5%, then that means you have 100 grams of the solution. That's what 3.5, we just did mass percent on the previous page. That's what 3.5 mass percent means. It means, remember, the grams over grams cancels out. That's how you end up with the percent. So it means you have 3.5 grams of your, in this case, the solute, NaCl, for every 100 grams of solution. Okay, I could have used other numbers, but 100 is a nice round number to use, and that's why we use it. Okay, so that's what we're starting off with. So let's look at what where we have to go. We have to get from grams of NaCl to moles of NaCl. Well, that's really easy. You know how to do that using your molar mass conversion. Okay, that's an easy one. Then we have to get from grams of solution to liters of solution. That one's a little bit trickier, but let's first of all take care of the moles of NaCl. So we're going to multiply 1 mole of NaCl for every 58.44 grams of NaCl. So grams of NaCl cancels out there and there. We end up with moles of NaCl, moles of NaCl. So we're all set on the numerator on the top there, okay? Now we have to get from grams of solution to liters of solution. Okay, well, we have this conversion up here. And I'm going to do this up on the top so it doesn't clutter up the equation down here. But we want it in liters, not in milliliters. We have grams of solution, milliliters. So what I'm going to do is I'm going to say that, well, I'll do it up here. 1.027 grams of solution for every 1 milliliter of solution. And all I want to do here is convert that milliliters to liters. So there's 1,000 milliliters of solution for every liter of solution. All that is a simple milliliters to liters. It doesn't have to be a solution. It could be of anything, but we're interested in the solution. If I do the math on that, I end up with, and I'm going to go ahead and write it down here now, I end up with 1,027 grams of solution for every 1 liter of solution. Just stop and think about that. If I had just a little over 1 gram for every milliliter, if I take 1,000 times this volume, I'm going to end up with 1,000 times this number of grams. So instead of 1.027, I end up with 1,027 for every liter. All I did was really multiply both of these by 1,000, okay, and converted it there. Okay, so now this is really good. We're at liters of solution here. And look, so liters of solution is what we want on the bottom. Moles of NaCl is what we want on the top. Now, hopefully grams of solution, well, there it is. It cancels with that and with that. So they cancel out. So the only things left standing are that guy and this guy, and that's the answer to our problem. So now we just have to run the numbers, and the numbers would give us 0.615 moles of NaCl over liters of solution, or again, the way to write it if it's molarity is 615 molar. Forgive me. Okay, so molarity is 0.615 molar. Okay, there you go. All right, go ahead and do the next one. It's done exactly the same, but cover up this solution, okay? Cover this. First of all, study this one, and then try to do this one, cover it up here, and try to do this one without looking at it, okay? So here we go. I'm going to go ahead and let's knock this down. So we have, again, we have 2.27 grams per milliliter. So that means the density. I'll write it way over here. Density is 2.27 grams of solution. That's your salt water for every 1 milliliter of solution. All right. So let's go ahead and write the equation then. That's actually not part of the equation yet. Okay, so let's go ahead and write the equation. We have a mass percent of 5.72. So let's do what we did up here. That means we have 5.72 grams of solution, because that's the density of the entire solution, for every grams of, I apologize, of sodium chloride for every 100 grams of solution. That's what mass percent means. Okay. Now we're going to multiply that by, we're going to take care of the grams of NaCl to moles of NaCl, because we need to end up way down here with moles of NaCl for every liter of solution. So let's take care of converting grams of NaCl to moles of NaCl, and that's going to be 1 mole for every 58.44 grams. Okay, so grams of NaCl cancels. Okay, we have moles of NaCl, that's what we want on the top over here, so that's all good. Okay, now I'm going to take this and I'm just going to take that you remember that we simply multiplied this by 1,000 and this by 1,000 to get our conversion. So that gives us 2,270 grams of solution for every 1 liter of solution. Okay, I just multiplied this by 1,000 to get that. Okay, same thing we did up here, right there. See it? Just did that, multiplied by 1,000. Okay, good. So now we got grams of solution here that cancels and cancels with this, and we're left with liters of solution on the bottom, which is what we want. We have moles of NaCl on the top, which is what we want. So now we just have to crunch the numbers, and when you do that, you get 2.22 molar. Moles per liter or molar, okay? Okay, and that takes care of that. So again, study this, follow these relationships, write this problem out, these last 2 problems, write out a couple of times each, at least 2, 3, 4 times. Get to where you're really comfortable with how they got set up, how the units canceled. They're not easy problems. They're about as difficult a problems as you'll be given with this, and we're hitting them really early so that you have a chance to expose your mind to them. You'll only be seriously tested on these in about 3 or 4 weeks. Okay, 6A, let's keep going. What is the molality? So we're looking for molality of lead ions in a solution that is 400 parts per million of lead ions. Okay, so molality is going to be moles of lead, which is Pb, and that's for every 1 kilogram of, and it doesn't say what it is. If it doesn't say what the solution is, you can assume it's water. Okay. So 400 parts per million means parts of what? Is it number of molecules? Is it moles? It's actually mass in grams, okay? So it means you have 400 grams of PB for every 1 million grams of the total solution. And I'm going to write that out. Scientific notation might be appropriate for a number this large, but I just want to be sure we're really clear on what the number is we're dealing with. So that number is 1 million, and that's grams of solution. Okay. All right, now what do we do? Well, grams of solution, we need to get to kilograms of water. That's our solvent. That's not the solution. That's just the solvent. So how do we do that? We have to do a conversion between the grams of solution and the grams, before we get to kilograms, even the grams of solvent, of water. How do we do that? Well, think about it. You got 1 million grams of solution, and you got 400 grams of lead. So if you want to know how many grams of water you have, H2O, you subtract. 1 million minus 400 grams of PB will give us 999,600 grams of H2O. So that's the grams of our solvent, which is what we want at the end. We want solvent, H2O. Okay, so what we can do is then do that conversion. There's 1 million grams of solution for every 999,600 grams of H2O. So you see we're getting close. We got grams of H2O. We want to end up with kilograms of H2O. So now what we simply need to do is we need to convert and say that there is 1,000 grams of H2O for every 1 kilogram of H2O. Okay, so now grams H2O cancels with grams H2O, gram solution cancels with gram solution. We have kilograms of H2O on the bottom. The only thing left to do is we need to get from grams of PB to moles of PB. Okay, and in order to do that, and you should do this at the beginning, you create your molar mass conversion. So for lead, that is going to be 1 mole of PB, lead. Just go to your periodic table. It's just a single element, so you just read the number off. It's 207.2 grams of PB, right off the periodic table. Okay, so now we just put that into a ratio so that grams cancels out and moles ends up on the top. So it's times 1 mole of PB for every 207.2 grams of PB. So now grams of PB cancels here, and we're left with moles of PB over kilograms of H2O. I didn't leave myself very much space to write the answer, so I'm going to come down here and do that. And the answer that you get is, the one shown here is 0.00193, and it's a molality, so it's small m. And that's the answer, okay? That's the number that would go up there. All right, there you go. Study that problem. That's a challenging problem as well. You will not see a problem on a test like this for several weeks. Okay, let's go on to 6B. First of all, scratch this answer. It was did not correctly put the correct answer there, so we're going to do it now. Okay, so here we go. Study that one and then see if you can do 6B. It's the exact same problem with different numbers. See if you can do it. Okay, so here we go. So we're going to start off with 67,000 grams of, and I didn't change the element, it's still PB, Now this is for every billion. Again, it would be more proper to write this in scientific notation, but I'm just going to write it out. It's got 9 zeros. Okay? And that's grams of solution. Okay, and remember over here, we want to end up with moles of PB for every kilogram of solvent, which is H2O. Okay, so now what do we do? Well, we have grams of solution. We need to get it into kilograms of solvent. So we got to relate. The grams to kilograms is not hard to do. We got to get from solution to solvent. So we have to have that relationship. So we do the same thing we did last time. We say a billion grams of solution minus 67,000 grams of PB, of lead, is going to give us our grams of water. And that number is going to be a big number, 933,000. Okay, that's a 3 right there. Okay, and that's grams of H2O. Okay, so now we come back here. We know there's that many grams of H2O for every billion grams of solution. So we just come up here, and keep in mind when you do your math, a billion on the top and billion on the bottom are just going to cancel each other out. You don't even have to punch them into your calculator. A billion grams of solution for every 999,933,000 grams of water. Okay. All right, and grams to kilograms, same thing it was before. There's 1,000 grams of water for every 1 kilogram of water. Okay, and finally, so we got the kilograms of water. This cancels with this. Grams of solution, grams of solution. Now we have grams of PB. We got to get moles of PB. It's the same conversion we did in the previous problem. There's 1 mole PB for every 207.2 grams of PB. Okay, moles. The grams with PB here goes all the way back to the beginning of the problem to cancel grams of PB there. So we end up with moles of PB over kilograms of water. That's what we want. And when you run the numbers on that, that's going to give you 0.032 moles per kilogram, or molal, small m. Okay, and that's how you do that one. Okay, let's keep going. What is the mole fraction of sucrose in a solution that is 5.84 molal sucrose? Okay. Okay, so here we go. So what does molal mean? It means that there's 5.84 moles. And just to abbreviate this, we don't need to know the molar mass of sucrose in this problem. Oops, what did I just do? We don't need the molar mass. You don't know that at this point. You might need it, but I'm just going to tell you, you're not going to need that. I'm just going to write SUC for sucrose rather than write out the chemical formula, which is kind of, a little bit long to have to keep writing. And that's for every, if it's molal, it's for every 1 kilogram of, and we're assuming this is in water. If it doesn't say, you assume it's water, for every kilogram of H2O. Boom. So we need to get, if we want mole fractions, everything has to be in moles. So we have moles of sucrose. The only thing we need now is moles of water, okay? So 1 mole, I'm just going to do this over here to the side, of H2O equals 18.02 grams of H2O there, okay? And if this is molal, that means for 1 kilogram of H2O. So that's 1,000 grams. So the way we figure out how many moles of water is in 1,000 grams, 1,000 grams times 1 mole of H2O. Now notice I'm not writing a big long equation. I'm doing a bunch of little small equations here. Over 18.02 grams of H2O. Okay, and when you do that division problem, you end up with 55.49 moles of H2O. Okay, so now we know how many moles of H2O. We know how many moles of sucrose. That was given to us right at the beginning. So now we just have to create a mole fraction for sucrose. So remember, it's moles of sucrose over moles of the whole thing, the sucrose and the water together. Okay, so I'm kind of working a little tight space down here, but let's go ahead and do this. So moles of sucrose is 5.84 moles sucrose divided by 5.84 moles of sucrose plus 55.49 moles of H2O. Okay, so it's, and remember, it's a fraction, it's not a percentage, so it's just simply going to be a fraction problem, and what you end up with there is 0.091, either, 951 or 952. I think it could have been, I can't remember, but we're going to say it's that. And it's a fraction, so it has no units of measure. It's just, that's the answer, okay? It's just a fraction. That's the fraction of that solution that is made up of sucrose. Okay, next one down, we're going to do the same thing. So we got to see if you can do it on your own. Study this problem, pause, cover up this problem, and see if you can do this one by itself. It's just different numbers. This answer is incorrect, so let's scratch that. Okay, so here we go, 6.91 moles. And again, I didn't change it, it's sucrose, SUC, over 1 kilogram of H2O. So since we want mole fractions, everything has to be in moles. So that means we have to turn a kilogram of water into moles. We just did that, and that is 1 mole H2O. Let me correct that. It's 6.91. I'm sorry, I had it right the first time. Okay, we know that 1 kilogram is going to be, as we did the conversion in the previous problem, so I won't do it again here, is 55.49 moles of H2O. In other words, why are we saying that? Because we know how many moles of sucrose we have for every kilogram, and that's how many moles a kilogram is 55.49. So now we know the moles of both of these. So to know the mole fraction, okay, so to get the mole fraction, it's the 6.91 moles of sucrose over the moles of sucrose and the moles of water together, 6.91 moles. Okay, and when you run the numbers on that, you should get 0.111. Okay, so a little more than a tenth of that solution is the sucrose. Okay, and again, that's dimensionless, it's a fraction, so that's that. Okay, keep going. All right, I did not show you the equation for this. This is a dilution problem, so I'm going to show it to you now. It says if 1.5 liters of 5 molar solution of sodium chloride is diluted to 6 liters, what is the molarity of the new solution? So in other words, you want to make it weaker. Think of if you've made lemonade and you put too much lemonade powder in and you want it to be a little weaker, it's too strong and too syrupy tasting. So what you do is pour more water in, and that's called diluting it. And it's a really simple formula. As long as you're dealing with moles and liters, volume and liters, and then moles, okay, or molar solution, not moles, but molar solution. And it's basically this. Before you have a molarity. In this case, it's 5 molar right there. So we're going to call that the before molarity. That's molarity number 1. And the volume before, which is 1.5 liters. So that's volume 1. And it just simply is an equation that the molarity after, that's molarity 2, and this is the after side, after you've added some water. Well, this volume times this molarity will equal this volume times this molarity. So at that point, it's just a pretty easy problem. The volume is 1.5 liters. The molarity is 5 moles. Molar. And it wants to know what is the molarity. It wants to know the new molarity, so we'll call that M2 equals the volume after, and that's 6.0. So you added enough water to go from 1.5 liters up to 6 liters. Okay, up to 6 liters. And so if you just do the simple math on that, then the second molarity, the molarity after you've added the water, is going to be 1.25 molar. In other words, think of it this way. You went from 1.5 liters to 6 liters. That's 4 times as much water. So you're going to end up with 1/4 the molarity you had before. If you start out with a molarity of 5, it's going to be 1/4 of that is 1.25. So it's just an inverse relationship. And that's all there is to that. Okay, 8B is just like 8A. It's a pretty easy problem. So we have a 6.5 molar solution. And we have 2.3 liters of it. Okay, and we're going to increase that from 2.3 liters up to 4 liters. So we want to know what's the new molarity going to be. So the molarity, the second molarity after the dilution, and dilution means you're adding water to it, is 4.0 liters. And if you just do the simple math on that, very simple algebra, you get that the molarity after is 3.74 molar. Okay, good, let's keep going. Okay, so 9A. By the way, these are simply references to myself as to where I got the problem from, so you don't need to worry about that. A solution is made by dissolving 4.35 grams of glucose, and there's a chemical formula for glucose, you're going to need that, in 25 milliliters of water at 25 degrees C. Don't worry about the 25 degrees C, except it's just a very standard temperature, okay? We'll talk about why that would be significant later on. Calculate the molality of glucose and water. So here's what we're trying to shoot for. If it's molality, it's moles. And I'm just going to abbreviate it as glucose, GLU, rather than writing that long formula every time, over kilogram of H2O. Okay. Now, what do we start with? So we come way over to the left with what we start with. We start with 4.35 grams of glucose, okay, C6H12O6, for every, it tells us 25 milliliters. So we know we have that concentration right there. And that's of water, of H2O. Okay, so let's look at where we're trying to get. We're trying to get from grams of glucose to moles of glucose. And we're trying to get from milliliters of water to kilograms of water. Okay, So you'll notice that this is in a measure of volume. Milliliters is a measure of volume. Kilograms is a measure of mass. So we need to know some relationship between that. Well, first, let's take care of the numerator. Grams of glucose to moles of glucose. So let's go ahead and get our molar mass relationship. 1 mole of glucose, which is this thing up here, equals 180.18 grams of glucose. Okay, so let's go ahead and use that, and let's take care of that, the numerator. So it's going to be 1 mole for every 180.18 grams of glucose. Okay, grams of glucose cancels here and here, and we end up with moles of glucose, moles of glucose. So we've taken care of the numerator. Now we got to deal with this. Milliliters to kilograms. Well, remember we talked back at the very beginning that there's a relationship if it's pure water between mass and volume. And that relationship is that there's 1 milliliter, this is only true for water, of H2O for every 1 gram of H2O. That mass-volume relationship is a very nice one and applies only to water. So now we got canceled milliliters of H2O, and now we got grams of H2O on the bottom. We just have to get it into kilograms, and that's not very hard. It's 1,000 grams of H2O for every 1 kilogram. So that might have seemed like a little tricky maneuver right there, but you know what? You'll get used to it as you work problems. You'll say, okay, that's like a tool in your toolkit for the future to know that you can use to figure out this problem. Okay, so we've got kilograms of H2O here, and that's the last man standing on the bottom. We have grams of H2O here, grams of H2O. We had moles of glucose is the last man standing on top. So moles of glucose over kilograms of H2O, and we're good to go. And the answer we're going to get is 0.966 moles of glucose, or you can say 0.9, in fact, you should say 66 small m, molal. Okay, there we go. I hope you're feeling a little bit better about these. That these are tricky at first, but once you see enough of them and do enough of them, it's really doing them yourself that they start to sink in. Okay, 9B is like 9A. So we've got 7.2 grams of glucose and 35 milliliters of water. So let's go ahead and write that down. 21 grams of glucose for every 35 milliliters of water. And again, I would stop and look at 9A, see if you can remember the technique, and then see if you can do this one by yourself. That's the only way you eventually get to where you're fully competent at these problems. Okay, so now again, we're going to just go ahead. We know we want to just write down what we're shooting for over here. It's moles of glucose for every 1 kilogram of H2O. Okay, grams of glucose to moles of glucose, we know how to do that. We've already computed the molar mass conversion. It's 180.18. Okay, so now we've taken care of the top, the numerator's taken care of. Now we got to get milliliters to kilograms. So we just remember that simple relationship, 1 milliliter of water, only of water, equals 1 gram of water. Okay, so we got milliliters, and I should have put down here milliliters of H2O because that's what the problem told us. So milliliters H2O cancels milliliters of H2O, and now we got to get grams into kilograms. That's easy enough. 1,000 grams H2O for every 1 kilogram H2O. Okay, and we have grams of H2O, grams of H2O. So the last man standing is kilograms of H2O and moles of glucose right there. So we just go ahead and do our calculation, and you should get 1.14. Okay. Again, redo these problems. Don't just do them once. Do them over and over until it just becomes natural for you. Okay. Last problem set here. Solution is made by dissolving 13.5 grams of glucose in 0.1 kilograms of water. What is the mass percentage of the solute? Well, you should look at this and say this is going to be an easy problem because I'm looking for mass percentage and everything is already in mass. Okay, it's expressed in some unit of mass. So this isn't going to be a hard problem. The only thing we got to do is we got to convert kilograms to grams. We can't deal with grams and kilograms. You've got to convert one to the other. You could go in either direction doing that, but we're going to convert kilograms to grams because we're used to working in grams. So we're going to say 0.100 kilograms of H2O times 1,000 grams for every 1 kilogram. So that cancels with that, and you got 0.1 times 1,000 equals 100. So it's 100 grams of water. And if you could do that one in your head, feel free to. You didn't have to do this. If you said, I know that 0.1 times 1,000 is going to be 100, that's fine. Okay, so here we go. So now we got everything in grams. We got water in grams. We've got glucose in grams. What's the percent of the solute? So it's going to be 13.5 grams of glucose divided by the mass of everything put together, 13.5 grams of glucose plus 100 grams of H2O. Okay, not too bad. And then I always forget, but don't you forget. I'm not taking the test, you are, times 100%, okay? So there you go, and if you do that, you should end up with 11.9% glucose by mass, okay? That's a percent sign if it doesn't look like one. Okay, we're almost home here. So 0.02, you compute that the same way we did up above, 0.200 kilograms times 1,000 grams for every 1 kilogram. That cancels with that, and you end up with 200 grams of water. Okay, so we go ahead and put the 29.5 together with the 200 grams, and we want to know 29.5 grams over 29.5 grams plus 200 grams times 100%. And when you do that, you end up with 12.9. So 12.9% by mass glucose. Okay, guys, it's a little bit long. We're over an hour now, but practice these. This is going to be your really important subject when you, especially when you get back into actually doing real labs. You got to understand how to compute and manipulate solution and concentrations. Okay, so we'll work on this also, but you should have all these problems done by the time you walk into the class on Monday. Okay, it's now Saturday afternoon. So get these things done for Monday and have a nice rest of your long weekend. Bye-bye.